Okay, first I want to thank this organizer for such a nice summer school. And the organizer gave me a very huge topic, but I would like to limit the scientific objective to the implication of cosmic ray sciences. Because, astronomy, although this ultra-high energy astronomy is quite new, but the scientific objective is still very diverse. So in this talk, in this lecture, I will focus mainly on the implication to science, cosmically related science. Okay, so this is the outline of my lecture. I think at the first lecture, I will mainly talk about the background, the field and status of the gamma ray astronomy, and something about cosmic rays. I think most of this content is more or less covered by the former lectures, but I will stress this again. And then tomorrow I will talk about this status and progresses and the future prospect of the ultra-high energy gamma ray, which is a brand new window and is quite active now. So let's begin with this gamma ray astronomy. So gamma ray basically is this photons with energy more than 100 keV or something like that. And this property of gamma ray is that our atmosphere, this Earth's atmosphere, is totally opaque for gamma rays. So they cannot penetrate at all. So to detect gamma rays, there are only two ways. One is to put the detectors in space, and another is to detect these secondary particles produced by the interaction of the gamma rays with the atmosphere. And so this is, I think, okay, so I guess not all the students have the background of astronomy, but this is our transparency of atmosphere to the whole electromagnetic wave band. So we see, in fact, it's only our atmosphere is only transparent for very limited band in the whole electromagnetic wave. And the gamma ray is kind of here, our atmosphere is totally opaque. Thus, there are two ways to detect gamma rays, as I mentioned. One way is to put the detector in satellite in space, and another is to observe the secondary particles produced by gamma rays interacting with the atmosphere. And another property of gamma ray is that the photon energy is so high that until now we didn't find any material can reflect gamma rays. So this means we cannot focus gamma rays and to do this, produce some imaging system like real optical telescopes. So in this sense, to detect gamma rays, we are still using a lot of this particle detection techniques. I guess it's already covered by these former talks. And thus, this gamma astronomy is, by definition, is a very joint subject between astronomy and particle physics. We begin with this so-called spade boson detectors. So this, in fact, we put these particle detectors in space. The famous one is Fermilab from NASA, and I also, this is put something, this Stampede satellite here. Of course, in principle, these gamma ray telescopes in space, they are basically pair conversion telescopes. This means these gamma rays, they interact with the material in the detector, and they are converted into this positron electron pairs. And we used this particle detection techniques to reconstruct the energy and direction of the incident gamma rays, and then we can do astronomy. So for this kind of space-bound detectors, they cannot be very huge, of course, because we have to put them in space, and they are very expensive. So the effective area of such detectors is only of the order of 1 square meters. But since they are not real telescopes, we don't have to focus the light. one big advantage of such kind of gamma ray detector is that they have very huge field of view. I think for this, most of this kind of space-borne detectors, they have a field of view of several stereons. This means they can monitor the sky, a huge portion of the sky at the same time. So in this sense, it's gamma ray astronomy. This kind of detectors, they are by definition a very good time domain detectors. And another thing in astronomy is so-called angular resolution. We use something like point spread function to describe this quantity. This means how we can resolve, how accurate we can resolve, or we can reconstruct the incident photon's direction. So for this kind of space detectors, this average value is about 0.1 to 1 degrees. So compared to this real optical telescopes, it's very bad, to be honest. This is, I think for this optical and its X-ray instrument, this value can be as accurate as several arc second. But for gamma rays, it's degree level. So this is our huge disadvantage. So comparing when you do this multi-wavelength or multi-messenger astronomies, this PSF in this gamma ray domain is always bad. Yeah, it's always worse than others. And since these are particle detectors rather than real telescopes, they can monitor in the sky continuously. They don't care about the weather. They don't care about this is night or something like that. Yeah. And the detection technology, I will talk about a little of the detection method, but this is not my major, so I will do it quite briefly. So the detection of gamma rays depends totally on the interaction of photons, of gamma ray photons with matter. So this is the cross section of photons in interacting with matter. So I think we should already have the concept of cross-section, right? So the higher cross-section means a stronger interaction. So it involves with energy. So here we can see different physical processes. So in this lowest energy band is dominated by this photoelectron absorption, and in MUA band, this Compton scattering begin to dominate, and this is where we built these competent telescopes to detect MUA gamma rays. And above probably tens or hundreds of MeV, this so-called pair production process, they dominate all the interaction processes, and that's why the current this major gamma ray telescopes in space is the so-called pair production telescopes, because they are running in this region. Oops. Okay, should go like this. Okay, this is just the basic idea of the Compton scattering and pair production. I will just show it here. We didn't talk the detail of this process. And about this history of this gamma ray astronomy, I mean, this is one thing we cannot escape is this so-called Compton Gamma Ray Observatory. In fact, this is a very huge satellite. We can see there are several instruments on board of this huge satellite, and one is COMTEL. This is the so-called Compton telescopes operated in this MUA band, and another is IGRIT, is the pair production telescopes operated in GeV band. And of course, they have some other things. This BIST is special designed for gamma rays, and also is kind of optical module. And this is the basic idea of how COMTEL works. It consists of two layers of scintillators, and this gamma rays, they can counter scattering with the material, and this counter scattered electrons will be recorded by these scintillators. But for Compton scattering telescopes, there's a big problem is the scattered electrons, because they are very easily to scatter with the material again. So it's very hard to trace the full trajectory of these scattered electrons, as well as the true direction of the incident photons. So this, although this, I think COMTEL, even until now, is kind of this most, it's not working now, but it's, in history, it's the most sensitive gamma ray instrument in this energy band. But it's, I mean, comparing with the instrument in other wave band, the sensitivity of COMTEL is much worse. It's at least 2 order of magnitude worse. So this means this MEV band is the worst detected band in the whole electromagnetic wave. And another is IGRIT. This is a pair production telescope. And in fact, the structure of this telescope is similar to the current Dampi or Fermi-LAT. So it consists of mainly 3 parts. The first layer, the outer layer is the so-called anti-coincidence detectors. It's made of, basically made of plastic scintillator. And it can distinguish between charged particle and gamma rays. Because this is a gamma ray telescope, but we know this is, in principle, it's a particle detector. So we can detect these pairs produced by gamma rays. They can also detect all these charged particles in cosmic rays. We know there are a lot of charged relativistic particles in space. They called cosmic rays, which is the topic of our next session. And so to detect gamma rays, one big mission, a big task, a very essential task is to distinguish between charged particle and this gamma rays, which is neutral. So in space telescopes, it can be easily done by such kind of anti-coincidence detectors. And then the pair, this gamma rays converted to pair inside the detectors, and with this trajectory detectors, is in this IGRIT is some old-fashioned thing called spark chamber. I think a lot of people here should know this much better than me. And with this spark chamber, they can record the trajectory of the secondary electron and positron pairs. And then at the bottom is the crystal scintillator, which is a calorimeter, and all this energy will deposit here, and we can record this energy of the incident gamma rays. We have the energy of incident gamma rays, and we have this trajectory of secondary electrons and positron pairs, which can be used to reconstruct the direction of this incident gamma rays. So then, at last, we will have this direction and energy of this incident gamma rays, which can be used to do this astronomy.
So the upper spark chamber is not a very good radiator. I mean,
no. So this is very old one. I mean, this is IGRIT. This is in 1990s. So that's why it's not.
The probability converting into E plus E minus in thin chambers.
Yeah, of course. But I think they have some heavy, I mean, high density material between to increase the conversion. Yeah.
Okay.
Yeah. I think also Fermi-LAT and Dampi, they have this tungsten between these silicon layers. Yeah. So to increase this effective area or the efficiency. Yeah. So this is the sky map of IGRIT. In fact, this is the first all sky map above 100 MeV for our human beings. So although the angular resolution is not very good, as I mentioned before, but we can still see a lot of interesting things here. For example, this is the sky map in this galactic coordinate. So in the middle, this is our galactic plane. So we can see that above 100 MeV, this most bright feature of our sky is the galactic plane. And we have some very bright point sources. Like here, I think this is some, I guess it's Macaron something, 421 or 5001, I don't know. It's from some bright nearby AGNs. And also in the plane, I guess this one is this very nearby bright pulsars Vela. And Crab is somewhere here, I guess. So at that time, we have already detected 200 sources, 200 gamma ray sources. So with this, we can, I mean, to do astronomy, we need sources. So I think only from this time on, we have real gamma ray astronomy. And then the next generation, I mean, which is still in operation, is the Fermi-LAT. It's in fact structure is very similar to egret, but of course with some fancy new technology at that time. The trajectory detectors now is a silicon strip rather than a spark chamber, which can provide a much better spatial resolution, thus a much better angular resolution. And this calorimeter is now this CSI crystal rather than this former another kind of crystal to provide a better angular resolution. So this makes the angular resolution of Fermi-Latte is much better than egret. And so we have this much finer sky map from Fermi-Latte in the same energy band. So for Fermi-Latte, because of this much better angular resolution, thus much better sensitivities, it detected much more sources than egret. Until now, I think this number, sorry, is not correct. It's more than 6,000 now. We have more than 6,000 GeV sources detected by Fermi-Latte in the whole sky. And we have much finer description of this galactic plane. We can see here you see a lot of fine structures, and you can see by eye this is a very interesting, huge structure in this galactic center region, which is called Fermi bubble. You can see it by eye. In fact, it's these very huge structures. And another method, another technology is ground-based telescopes to detect gamma rays. So as I mentioned, our atmosphere is totally opaque for gamma rays. But we can detect these secondary particles produced by the interaction of gamma rays with these nuclei in atmosphere. So here is we need some concept is called extensive air shower. Because our atmosphere, in fact, is quite dense. So all these high energy particles, nevertheless, gamma rays or these charged particles, when they enter our atmosphere, they will interact with these nuclei, mainly this nitrogen, very quickly. And if it's a gamma rays, the dominant first interaction process, of course, is the pair production. They will produce this still very high energy electrons and position pairs. And these electron and position pairs, they can interact with these nuclei again via such as Helmholtz-Halon process and produce gamma rays. And they can also, because we have this geometrical magnetic field, so they can also produce with this magnetic field to produce lower energy photons as well. And these gamma rays will further produce with our atmosphere and produce further a lot of more pairs. And this process will keep going on until this energy of this gamma rays they are below this threshold of these pair productions. So this means if your incident particle has this high enough energy, they can produce a huge amount of these secondary particles. And due to this relativistic beaming effect, this huge amount of secondaries, they will arrive at our ground, this detectors in this ground level at a very short time period, such as maybe tens of nanoseconds. And for charged particles, the process is similar. They also produce a lot of secondary particles and arriving at a very short time interval. But the difference is this, because we have hadrons in these particles, so this the interaction process can be different. If we have hadrons, we expected there should be a lot of pions to be produced in the process, which will further produce muons. And so, of course, there are some further differences, but at the first glance, this most different things of these secondary particles produced by gamma rays or electrons or these hadrons is that in these hadron showers, we should have much more muons. And then this is the concept of the so-called extensive air shower, or EAS arrays, which are used to detect this secondary particle directly at some altitude. Of course, this altitude you chosen depends on this energy of the incident particles, because we can imagine if this incident particle, they have different energies, the shower will develop into this maximum size at a given altitude. It depends on this incident particle's energies. So I think this is the concept. This is a schematic figure of the last generation, this AS gamma experiment in China, in Tibet. And in the surface, we have a lot of this EAS array, which is kind of scintillators to detect these charged particles. And in the underground, we also have a huge muon hall to detect these muons. This is a kind of water Cherenkov technique. And currently there are several this kind of extensive air shower arrays in operation. For example, the largest one and currently the most successful one is LASSO in China. And we also have Hawk in Mexico. And this is Old Milagro. And here also very near Baikal, there is Taiga is also in operation. And compared with the space-borne detectors, the extensive air shower arrays, of course, they have different characters. For example, they can be very large. Because this is just particle detectors, we can put it on Earth. If we have enough space, we can put it as you wish, as large as you wish. And for LASSO, the occupation area is more than 1 square kilometers. And I think Taiga now is also, the first phase of Taiga is also kind of 1 square kilometers. And I've heard they have the plan to build it to more than 100 kilometers. And also, because they are also particle detectors, they have very large field of view. I think someone asked this question already in Lily's talk. In fact, this particle detector can record the secondary particles from every direction. I mean, but to facilitate effective this energy reconstruction and this direction reconstruction, sometimes we only choose a limited zenith angle. We cut in the zenith angle. We cut these very horizontal events because they are very difficult to reconstruct. And the PSF, of course, of this kind of telescopes, we can imagine is even worse because we are not detecting a single particle. We are detecting a fluctuation, the statistical this processes. So there are a lot of this statistical fluctuation in this detection, and of course the PSF is currently can only achieve about 0.2 to 0.3 degrees, and the annual threshold can be high. It can be lower. If you build it at a very high altitude, you can impressively detect very low energy particles. But currently, this is most of this ongoing instrument, their energy threshold is above 1 TeV, so they are only used to detect this very high energy domain. And of course, they can be used to do this continuous monitoring because this is part of the detectors. There are no these optical systems. We don't care about the weather. We don't care about this clear night. We don't care about the moon or sun or something else. So this is their advantage in this continuous monitoring. And but there is another technique in detect gamma rays from space. From this ground-based detector is called this imaging air Cherenkov telescopes. These telescopes, they are also detecting these secondaries produced in extensive air shower, but they are not detecting this secondary particle directly. They detect the Cherenkov radiation of these very high energy secondary particles in our atmosphere. So I think everyone here should know this Cherenkov radiation. If the charged particle they move with a speed higher than this light speed in this medium, they will produce this Cherenkov radiation. This secondary particles produced in this extensive air shower, they are also highly relativistic, so their speed is very near this speed in the vacuum, so can be higher than the speed in the atmosphere. Then we have Cherenkov light. And the advantage of this kind of technique is that they can increase the angular resolution significantly, because this Cherenkov light, in fact, you are taking a picture of this air shower, of extensive air showers, and you can do it at the same time from different angles, from different positions with several different telescopes. And then you can use the so-called stereo technology to reconstruct, and you cross these reconstruct directions to derive better angular resolution. I think this technique is also widely used in Taiga. Taiga has two different types of Cherenkov telescopes. I think a lot of students here should know it very in detail. Yeah, this is the concept of this stereo reconstruction, which can improve this angular resolution as well as this background suppression. And so there are several I think mainly three major IACTs in operation. It's HES, MAGIC, and Veritas. And there are huge plan of CTA, which is already built in north and planned in the south. They are going to build more than, I think, 100 Cherenkov telescopes with different size. And of course, with very fancy techniques and very expensive. And this kind of the most advantage of this technique is this best PSF in gamma ray band. In principle, they can achieve 1 arc minute. For example, I think CTA, they claim they can achieve this value, 1 arc minute in 10 TeV or something like that. But this is real. In fact, this is real telescopes. They are optical telescopes. They are this Cherenkov light. They are more or less this blue light, this blue optical light. And thus, to observe this Cherenkov light of secondary particles, this system can be only operated during clear night and without moon. So the duty cycle of this kind of system is much lower than this aforementioned extensive air shower detector. I think, for example, this lasso itself can be operated with a duty cycle of more than 95% or even higher. So it can be used for more than 8,000 hours every year. But for IACTs, even in this even in the best optical site, I think the average duty cycle every year can hardly be larger than 1,500 hours or even less. And with this two techniques, this ESRE and IACTs, we have detected about 200 sources in TeV band. I mean, most of them are from this ground-based telescopes. I think most of them are from this. In fact, from these IACTs, because before they have much higher sensitivities than this ESRE. And for example, this is one example of HES survey. HES detected 78 TeV sources in this galactic plane, but I think most of them are still unidentified. Of course, most of them are related to pulsars. This is something very interesting because this is also again confirmed by Lasso. We found that most of these gamma ray sources above TeV or even at higher energy, they are kind of related to pulsars. And and before the above is some very brief introduction of the history of this field, of this gamma ray astronomy. So here I also list some known or identified gamma ray sources. We have similar remnant, of course. We have detected GRBs. We have a lot of pulsar window nebula, especially above TeV. At least half of sources are related, are PWN or kind of related to pulsars. And of course, we can do this indirect search of dark matter with gamma rays. I think this is already covered in Zhang Lai's talk. And pulsar itself is also a gamma ray source. This is both pulsar and PWM, they're related pulsars, but they have different radiation mechanism. And at least we have this very extended diffuse emission in the whole galactic plane, and and other huge structure like this Fermi bubbles. And another thing I want to stress here is that gamma ray, by definition, they are investigating this so-called non-thermal universe. Because if you are talking about this thermal emission, this 1 GeV already corresponding to this temperature of 10 to 13. Sorry, the unit is wrong. It's 10 to 13 Kelvin. So such temperature can hardly be achieved. Although we have a lot of this high temperature plasma in our universe, but 10 to 13 is still something. You didn't find too many places in our universe that have such high temperature. And this is only 1 GeV gamma rays. If it's higher energy, it's really impossible to produce in these thermal processes. So these gamma rays, they are, by definition, they are exploring this non-thermal process in our universe. And there are also, of course, there are some relevant radiation mechanism in gamma rays. This is already, I think, reviewed in detail in Lily's talk. And here I just mentioned some most relevant ones like this. They can more or less be divided into two categories. One is so-called leptonic processes, which is inverse Compton or Boehm-Hallon of relativistic electrons. And another is this hadronic process, which is this from the neutral pion decay from this pp interaction or p gamma interactions. So both this leptonic and the hadronic processes, they are related to this highly relativistic particles. And so these gamma rays, if we see gamma rays, for sure there are some very extreme energy injection and acceleration processes of these highly relativistic particles. So this idea turn our topic to the next session, which is the cosmic rays. So what is cosmic rays? Cosmic rays is, if you want to explain this word in one sentence, it's relativistic charged particles in our interstellar medium, right? So they are charged particles and they are very high speed. They are moving in speed nearly to the speed of light. And in fact, they are very important in our interstellar medium. So okay, so probably I should explain this interstellar medium at first. This interstellar medium is this, you can imagine it's all these things between the stars in our galaxy. So it's not vacuum, right? We know it's not vacuum in the universe, although the density is very low, but there should be something. The space between the stars is occupied by this thing called interstellar medium. And what is the interstellar medium? Of course, we have this very sparse gas with a density of about 1 atom per cubic centimeters. We have a very weak magnetic field of several microgauss. We have these photon fields, which is, we have CMB, of course, and we have also other photon fields in our galaxy. We have these photons radiated from the stars and radiated from this dust, which is heated by the starlight. So we have this so-called interstellar radiation fields. And then we also have this cosmic rays. This is the relativistic particles. And all these components, they contribute in principle a similar amount of energy densities, which is about 1 electrovolt per cubic centimeter. So everything contributes nearly the same amount. And the cosmic rays itself, in fact, is very important in this SM, because we know the stars, this major component of our galaxy stars, they are formed in interstellar medium. And in this star formation processes, these cosmic rays play a very important role. This is because these stars, they are formed in this very dense phase of SM. This so-called this giant molecular clouds, the density there can be as high as 10 to 6 or 10 to 7 atoms per cubic centimeter, which is much higher than the average value in the SM. And in such dense regions, this low energy photons, they cannot, or even X-rays, they cannot enter into these dense regions because of this absorption and shielding. So only these high energy particles, charged particles, these cosmic rays, they can enter into this very center of this dense giant molecular clouds where the star form. So in fact, in this very center of this dense cores where star forms, it's this cosmic rays, they dominate this temperature, this heating of gas and this ionization of the gas. So in this sense, this cosmic rays is this this initial condition of star formation. Although this is a rarely, yes, this is for sure. I think they admit that, but
I can see the correlation, but how can you say it governs the star formation? I mean, if the star doesn't form because of the cosmic ray. You could say that the dense region, there could be also the origin of the cosmic ray, but it's not a chicken and egg thing, no? I mean, they are probably both eggs because there's a dense concentration of matter there.
Yes, but I mean, in this very this star forming process, they have some initial conditions. They have, for example, one very important parameter is this ionization rate.
Okay.
So this is, I mean, in this dense core where the star really forms, it's just determined by this density of cosmic rays. I think this star formation people says that. They admit that, but this is in fact not very widely, not very investigated in detail because in current study, they only set some value of cosmic rays and they just do their calculations. Yeah. Because it's nearly impossible to measure this cosmic ray, this density is there. So this is very difficult topic. Yeah. And cosmic rays, we have already a lot of direct measurement of cosmic rays, especially in the spectrum. We know it's in more or less a power spectrum in a very large dynamic range from 1 GeV to nearly 10 to 20 electrovolt. It's more or less power low, but of course we have some fine structures, in this spectral shape. And cosmic ray is a very important medium or this material to study this, to indirect search for dark matter. For example, when I was a PhD student, there's a very famous discovery by Pamela satellite is the excess of the positron fraction. And at that time, a lot of people argue that this is the smoking gun for dark matter annihilation. Although it's not confirmed, but I think it's still there. And another, for this cosmic ray itself, of course, it's very important. And so it makes sense to investigate where they are accelerated, where they are produced, and how they distribute in our galaxy, in our neighborhood. And okay, here's some history of cosmic rays. Cosmic rays is discovered by this guy, Victor Hess, in 1912. So this cosmic ray is a very old science. It's more than 100 years, but this is still not settled because we still do not know. Although we have a lot of ideas, fancy ideas, but we still do not know the origin of cosmic rays. We're not sure where they are accelerated, although I think Lily already stressed that supernovae remnant is the best site. But I'll show later, even for supernovae remnant, we have some problems. And at the very beginning of the history of cosmic ray studies, they are used to study particle science because at that time, I think we human beings, we don't have accelerators, and we can only use these cosmic rays to find these new particles. For example, a lot of these elementary particles like positrons and muon kaons are discovered in this gamma in cosmic rays. And this is the kind of current status. I think every cosmic ray people they have to show this figure, which is the maximum energy of observed cosmic rays is 10 to 20 electrovolt, which is a lot of order of magnitude higher than this particles accelerated by this man-made these accelerators. So this means this nature is much more powerful than our human beings.
But this is not a fair comparison.
Yeah, I know. This is not the same as this, the center. Yeah, you're right. I know. Of course, I know. But I mean, so that's why I show this cosmic ray. They like to show this, but this is not very fair. You're right. Yeah. And okay, so we have a very nice measurement of spectrum in a very huge dynamic range from 1 GeV to 10 to 20 electrovolt. It's 11 order magnitude. It's more or less a power law. Of course, you have some fine structures, and the first very significant this spectral shape is the so-called Ni at about 100 PeV. So there are some. So currently there are some consensus that at least to the Ni, all these cosmic rays should be accelerated by our galactic sources. And of course, this is not the only reason. The true reason is that this. If you consider this 3 microgauss magnetic field, this Lambda radius of PeV charged particles is kind of several parsec. It's much smaller than the size of our galaxy. So with this energy, below this energy, this cosmic ray should be confined inside this galaxy. They cannot escape. So if we observe these PeV particles, they are for sure to be accelerated within our galaxy. And here I show some idea of this acceleration of cosmic rays. I think this will be covered extensively by Evgeny's talk, so I will go very briefly. So currently we believe this most efficient acceleration mechanism of this so-called diffusive shock acceleration, for example, in this supernova remnant. The supernova exploded, and this remnant they expanding in a very high speed, and they form shocks interacting with this interstellar medium. And the so-called diffusive shock acceleration means that these particles they cross this shock front back and forth, and in every encountering they gain energy. And within this process, these thermal particles can be accelerated, and they can form a power law tail, and this is where our relativity particle comes from. And another thing is that our magnetic field in the ISM, we have this ordered magnetic field, and we also have a very the so-called turbulent magnetic field, nearly as strong as this regular magnetic field. And because this cosmic ray, they are charged particles, they more or less they should propagate along these magnetic field lines. And since we have this turbulent magnetic field, they are turbulent both in this in the sense of timing or in the sense of this spatial. So so from some simulations, we can see that this propagation of this cosmic rays, they are kind of follow this randomness of this magnetic field, and they can be effectively described as some kind of diffusion process. Just think you are this atom of sugar. There are sugar is diffusion in this coffee. It's the same process of cosmic ray propagation in our galaxy. So you can imagine this will be, after they escape from their source, they will be more or less homogeneous in a much larger scale because of this process of diffusion. And in our own galaxy, we have kind of this phenomenological description of the whole picture of diffusion. And of course, I think really mentioned yesterday, this can be described by some very fancy numerical models such as Garaprop. They are solving this partial differential equation, including all these physical processes like escaping, like diffusion, and like cooling and spallation. Everything is involved there, and you can solve this equation numerically and derive some very nice results. But in fact, for at least for this cosmic ray protons, this cosmic ray, the major component of cosmic rays, we don't need to worry too much about this energy loss in this process, and protons, we don't care about the spallation. So the diffusion of this cosmic rays, in fact, can be described in a very simple model. So this is they are diffused in a very extended halo. This halo, the size of the halo is also tuned by this measurement of cosmic rays of secondary cosmic rays. And now it's believed that this halo of this cosmic ray propagated in our galaxy has a height of about 4 kiloparsec. And this is purely phenomenological. We don't know the reason. Because this height is much higher than this scale height of our galactic disk in each sense, in every sense. We have the galactic disk of stars. We have a galactic disk of this H1 gas or H2 gas, but their height is all their height is much smaller than the size of this cosmic ray halo in this phenomenological model. And we have kind of then in this halo we inject this cosmic rays with a power spectrum, and this is kind of expected from this diffusive shock acceleration. And this confinement, and then we confine these injected particles in this huge halo. This confinement time is also energy dependent, and the injection they kind of get balanced with this escaping or confinement, and we can have a steady state spectrum, which is this injection term times this confinement time, and then we get a steady state primary spectrum, which should be softer than the injection spectrum because of the energy dependence of the confinement time. And for secondary particles is not accelerated, is not injected in this term. They are produced by the interaction of this kind of steady state primary particles with this SM. So their steady state term, they have another, they have another softening. So in this sense, we can always constrain this energy dependence and confinement time from just simply by using this secondary to primary ratios, which can be measured very accurately by current instruments such as AMS. And also, this is kind of a basic picture and ideas of this cosmic rays acceleration and propagation. And of course, we can measure the spectrum and direction of this cosmic ray directly. We have this so-called cosmic ray direct detection laboratory. And since this cosmic ray, they are similar to gamma rays, they cannot enter our atmosphere. So there are also two ways to detect them, and similar, it's very similar. Everything is similar to gamma rays. So this is why I want to combine this cosmic ray and gamma rays, because they are so related. Not only this cosmic ray itself is a very important scientific objective of gamma ray astronomy, and another thing is that their detection technology is nearly the same. In fact, every gamma ray telescopes can be regarded as cosmic ray detectors. And for example, this is the we also go here. This is we showed this structure of Fermi-LAT, and here is the structure of DAMPE. DAMPE is designed for and optimized for detection of cosmic ray electrons, but we can see this structure is nearly the same as Fermi-LAT. They have this anti-coincidence, this detector, which is plastic scintillators to distinguish this charged particle and the gamma rays. And we have this silicon tungsten tracker to to record this trajectory of the incident particles. And we have a very huge this calorimeter, which is a BGO crystal. It's not CSI. It's not a crystal to achieve a better energy resolution. So you can imagine, although this is optimized for cosmic ray detection, of course it can detect gamma rays. This is no problem. Yeah. So, and they have, but for cosmic ray detectors, we have basically two types. One is this damping-like or Fermi-like. This is called calorimeter because they don't have magnetic field inside. Another more fancy one is this AMS2, and they have the magnetic field within their detectors. So with this magnetic field, they can measure this mass to charge ratio directly, and so they can measure these isotopes. But with this kind of, although you can measure the charge, but you can only measure the charge. You cannot measure the isotopes. You cannot distinguish this 12 carbon or 13 carbon. But AMS can do that. Yeah. Okay, and another is AMS. I'll go brief quickly. And so here I show some recent very interesting results of this direct measurement of cosmic rays. So this measurement of cosmic spectrum already go into this, we call this accurate astronomy regime. So I think thanks to this technology of these particle detectors, the measurement of all this of AMS and damping, they can achieve an accuracy of several %, which is, I mean, in astronomy this is not very common. It's quite rare. You know, in astronomy we always say this. We always do a lot of order of magnitude estimation, but in cosmic ray measurement, this accuracy already achieved several % level. For AMS, I think even 1 or 2%. And so one thing is that we found this hardening of cosmic ray proton spectrum in hundreds of GeV. This is kind of in conflict with our former assumption that we have a pure power law spectrum. So but this is expected. I mean, as your accuracy increase, you always expect a lot of fine structures, and it's but of course but we still call it kind of an anomaly of this cosmic ray detection because it's not explained. Someone attributed to this some local cosmic sources, which has a different character with this major source populations. But it's not settled. It's still an open question. And another is of course, this is a very famous positron, the electron excess. And I think this is firstly discovered Pamela, and then it was confirmed by AMS and with a much higher statistics and accuracy. And now it's still going on, I guess. And so the interesting things here is in a standard model of cosmic rays, these positrons is pure secondaries. We don't have the primary acceleration set for positrons. It can only be produced by this interaction of this primary cosmic ray, like this cosmic ray protons interaction with this interstellar medium. And this positron itself, they have very strong cooling because they are also electrons, they are very light, so their cooling effect is very significant. So we expect a very sharp or very soft spectrum of these electrons. And I mean, even in these fractions, even in positron over electron fractions, we expected a very quick drop against the energy. But in fact, instead, we observe increasing. So I think someone argued that this is dark matter. But of course, there are some interesting things of this scenario because I think the energy is a WIMP. The WIMP is this energy range. But I think the cross-section needed to explain this is much higher. We need a lot of fine-tuning like this somofore enhancement or local structure boosting.
May I ask you a question?
Yes.
When these results appeared back to 2008, I remember that very quickly it was interpreted like secondary interactions within the detector. After that, they did not follow the progress. So is this idea ruled out? Now people consider this as a real dark matter?
No. I think it's still under debate. It's not settled. I think still someone investigated in dark matter scenario.
You're talking about the secondary interaction in the detector?
In the detector, just normal cosmic
Ah.
rays producing positrons.
This is out.
Oh, okay. This is out. Yeah.
This is out, for
Yeah.
sure. I mean, this is definitely positron,
Primary.
before the enter.
No, not primary, but yeah, before the enter. Yeah, it's the. Yeah, this is the positron in ISM. It's the not positrons in detectors. Yeah. This is confirmed by other experiment. This is okay. Yeah. So it's still I think it's still an open question. Although it's not as popular as 10 years before, but it's still an unknown. And another interesting thing is that we found a uniform index of protons, antiproton, positrons, and this is very strange because we know this protons is primary and antiprotons is secondary, and positron is also secondary, and positrons they have the further cooling. So in principle, these three components they should have totally different indexes, but the recent AMS results seems to show that they have a quite similar index, and this is I think it's still not explained. Yeah. And the last thing is. Another thing, I don't know, this is a mystery for me, and I don't know whether if Evgeny have any idea is why helium is harder than protons. And this is, probably you can cover in your talk, and I think this kind of mystery. And recently there are also this, we call it anomaly, is not expected, but we observed that with high significance is that the boron to carbon ratio become harder. It seems we have another component of secondary because this boron is totally secondaries in cosmic rays, and carbon is primaries. So this we always, as I mentioned before, we use this boron, this secondary to primary ratio to diagnose this energy dependent confinement of cosmic ray in our galaxy, but they show some difference between this pure Pauli and this. We need. This means this propagation, this simple propagation model, need to be revised. So I list some of these open questions here for this cosmic rays. And this is above is the results from this space detectors, and of course we can also do that in. We can measure the spectrum of cosmic rays in this ground-based facilities, and of course, which is the same as this in gamma ray astronomy field. This, if we put these detectors on in ground, we can make it much larger to detect these much higher energies. So, I didn't show this. Didn't want to repeat this idea of since they are short. And for example, currently the largest this cosmic ray detector arrays on Earth is this Pierre Auger observatory, which is in Argentina, and the size is surprisingly very huge. It's more than 3,000 kilometers squares. Of course, these detectors are distributed very sparsely. They only have, I think, 1,700 detectors. But this is because they are designed to measure this highest energy end of cosmic rays. So they need this very huge exposure area. And so they are designed to observe this end of this cosmic spectrum, and which is this so-called GZK cutoff, which is predicted in 1960s, and which is caused by this cosmic ray interacting with MB via these delta resonances. And in fact, both this TA and Auger, they kind of observe some kind of similar features. And of course, there are different measurements with different size and different density of detectors are designed to detect the different energy band, and we now have several fine structures in this cosmic ray spectrum. as I mentioned, we have the knee at the PeV level, and we have the second knee, the ankle deep, and also this highest energy, GZK cutoff. And in addition to the spectrum, we can also measure this anisotropy of cosmic rays. Although cosmic rays, they are charged particles, they are well mixed in this interstellar medium. So they are more or less this homogeneous distributed in this arrival directions, but we still find some hint of this anisotropies. But this anisotropy is in a very low level. But in higher energy, it can be significant. For example, this T8 recently reported a very significant intermediate scale hotspot. It's something in another hemisphere, and we don't know what is that. Probably related to this nearby very high, ultra high energy cosmic ray sources. And in low energy band, we have this several instruments focused on this knee region, because the knee is the first significant spectral structure in the cosmic ray. So they are of this very prime interest for this cosmic community. So this LASSO experiment is designed especially for this region, for this knee region. I will not go through this detail of LASSO experiment, which I will go in tomorrow's talk. But here I want to show some recent results of LASSO on cosmic rays. We can see that they measure, they can achieve a very accurate measure of this knee region already. But although with this lot of this huge experiment, we have a very nice measurement of spectrum as well as this anisotropies, but it tells us nothing about this origin, or tell us very little about this origin or accelerator of cosmic rays, because as I mentioned before, these charged particles, they are well mixed in our interstellar medium, and the arrival direction is highly homogeneous. So in this sense, there are another way to measure, to investigate the origin of this cosmic rays by using the secondaries, but not secondaries produced in atmosphere. It's the secondary produced in SM or in their acceleration site. For example, we can use this secondary protons and neutrinos, which are neutral and can propagate ballistically, and we can use them to find this cosmic ray distributions and cosmic ray accelerators. So that's why I say this gamma rays astronomy, they are strongly related to cosmic rays, so I want to combine them together. And with gamma rays, we can in principle do these two kind of studies related to cosmic rays. The first thing is we can use this diffuse gamma ray emissions to investigate this cosmic ray distribution in our galaxy and to investigate their propagation effects. And another thing is this cosmic ray accelerators, they can be bright gamma ray sources, and we can use these gamma rays to locate this site of this cosmic ray accelerations. So here we begin with the diffuse gamma ray emission. So this is the GeV. I show three schematics here of this galactic plane. The first one is this gamma ray map, this raw gamma ray map. This what we observe in gamma ray band of our galactic plane. We can see there are a lot of bright point sources, but there are also these diffuse emissions. And if we subtract these non-point sources, such as these pulsars, and I think mainly pulsars in our galactic plane, and we derive more or less this diffuse emission, which, in fact, we can see by eye. It's very similar to the so-called dust opacity maps, which represent this gas Coulomb density. So this means most of this gamma ray in this energy band is produced by this cosmic ray interaction with this gas. So if we know the gas, we know gamma ray, we can produce a map of cosmic rays as well. We can produce this distribution, this energy spectrum, this energy density of cosmic rays all through this galactic plane, in principle. Yeah. So here we begin with some idea of this interstellar medium again, because this is a diffuse emission of gamma ray diffuse emission is strongly related to this topic. Of course, ISM itself is a very, very complex topic. I think it can cover the ISM. We have a lot of very thick textbooks on this. We cannot cover it here. But here I just write some take-home message here about the ISM. So the space between star dot vacuum, this is ISM. And we have gas, we have B field, we have dust. The dust is also important because that, although the total mass of dust, the dust is this graphite or some solid things, right? It's formed in this interstellar medium. The mass is only about 1/100th of the total mass, but they dominate the extinction. I mean, sometimes we cannot see the starlight from this very inner region of galaxy because the dust they just absorb all this starlight. And we have these radiation fields from stars, from dust, and from this, and also the CMB. So all these components they have a similar, at least we have cosmic rays. So all these components they have a similar this energy density of 1 electron-volt per cubic centimeters. And diffuse gamma rays are produced in this very complex ISMs. So we have a lot of radiation mechanism can produce these gamma rays. But as we can see it from this figure, the dominant process is the so-called pion decay process, which is the neutral pion produced in this inelastic collision of this cosmic protons with this ambient gas, this PP process, and they produce this pion decay gamma rays above 100 MeV. I mean, in the GeV band, this is the dominant process. Although there are a lot of other things, but in gamma ray astronomy, at this stage, we can ignore them. We only focus on this region. So then we know this is from this cosmic protons interaction with the gas. So if we know the gas distribution, if we know this gamma rays, we can have this cosmic proton distribution everywhere. So this is our goal. And of course, this ISM is complex, and we have different phases of gases. And from here, from the top to the bottom is with higher and higher densities. And in fact, stars are formed in this process. But for this gamma astronomy, we need to care mostly about this three different phases of gases: is ionized gas, neutral atomic gas, and molecular gas. The ionized gas is so-called H2 regions. They are always formed in this very massive stars. The total mass of this H2 gas, ionized gas in our galaxy is only a small amount, but it can be important in this active star formation regions, where we also believe these dynamic regions are also sources of cosmic rays. So in this sense, this H2 gas is also important in gamma ray astronomy. Another tool is this H1 gas, which can be traced by this 21 centimeter emissions. This is well known. This is the most important objective of radio astronomy, in fact. And we have currently a lot of this sky survey of this, and we more or less know this distribution of this kind of gas in our galaxy. And I think they occupy more than half of the total gas mass in our galaxy. And another is CO, is for the molecular gas, because the molecular gas itself is this molecular of H2 is symmetric, so they do not have dipole moment, so their radiation is very low. So in astronomy, we always use this carbon monoxide which is always accompanied with this H2 molecular hydrogen. We use this molecular to trace this H2 gas, and we use kind of this conversion factor to conversion this observed CO column to this H2 mass. And this H2 molecular mass are always in very dense, very clamp regions. This is where these stars are formed. So they are also very important in this gamma ray astronomy because they are this most prominent, most significant part in this gamma ray diffuse emissions. And at last, at last we have this dust emission or dust extinction, which we can use to trace all the gas in the line of sight. But the disadvantage of this dust is that we do not have distance informations. The former molecular lines, because they are lines, we can measure their velocities, and with their redshift or blueshift velocities, we can measure this specific distance of this cloud to us. But for dust, we do not have this kind of information. And with all these efforts to mapping all these gas phases, and with these gamma ray emissions, we can more or less derive this cosmic ray distributions in our galaxy, and this is this figure. And we can see this data point here is this, if you assume a cylindrical symmetry, we can measure these cosmic ray densities in different, this ring around this galaxy center. And it's quite surprising, it's quite unsmooth, and it's not peak in the galaxy center. We have a peak somewhere else. And also this hardening is not, the spectrum index is not uniform. We observe a hardening of this cosmic ray spectrum index towards the center. So I think I can stop here, and I will leave the next session.
Thank you very much. Okay, so please, questions.
Thank you for your talks. I have technical questions.
Mm-hmm.
When we work with the detectors in the ears, we understand some problems with work with him. And when you work with detectors in space, you have space debris, and how we work with this problem?
Sorry, we'll work with
This problem. Space debris.
I'm not sure I'm the correct person to answer this question, but to my knowledge, I get involved in Stampy experiment, and we have this kind of backup in every, important this parts of the detectors, and also most of this. Instruments, this detectors are designed to be more substantiable than on Earth. So that's why I think at least most of the spaceborne detectors they are in good shape, at least during their design this lifetime. Yeah. Oh, okay.
Other questions?
Thank you for the great talk. I'm not very familiar to cosmology, so I have just one simple question about the shielding effect of ISM. So I want to know, does the ISM exist all over our viewpoint from Earth to cosmic space, and does it put a restriction on the lowest energy of photons we can detect?
It also depends on the energy of your photons, right? And of course, this is it's not homogeneous. For ASM, we basically means this is a stellar medium. It's interstellar medium, so it's in our galaxy, mostly in our galactic plane. So this value is for the value I showed here. All this value here is the typical value in our galactic plane. If we look, away from the plane to for example, the North Solar Pole, something like that. You do kind of line set integrations. This densities is much lower. There are also something called circumgalactic medium. And also this is the medium between these different galaxies. And we also have this circumcluster medium. This is a medium between these galaxy clusters. They are much more sparse. So we have much fewer, the density is much lower there. So this is, I think.
Thank you. So does it still has a restriction on the lowest energy of photons we can detect, even from a more clear view angle?
Yeah, sure. This is the horizon of the photon depends on the energy. For example, because in different energy you have different absorption mechanisms. For example, in this ultra high energy gamma rays, these highest energy photons I will talk about later, the horizon is very limited. It's only several kiloparsecs. So this means in this energy band, you can only see things near our galaxy. Of course, lower photons, they can go further.
Okay, thank you.
Other questions, please?
Thank you for the lecture. I have one question. Can we distinguish protons and antiprotons, considering them as primary particles using grounded-based experiments, or is it possible just with space detectors?
This is a very good question. I didn't mention this. No, we cannot do that in this ground-based experiment. We cannot. If I'm wrong, someone maybe here can correct me. But to my knowledge, we cannot measure the charge in ground-based experiment. This can only can be only done in this space-borne satellite. Yeah. So that's why another issue here is that we can also not distinguish electrons and gamma rays for ground-based telescopes, for ground-based instruments, because they all generate this electromagnetic field shower. So in this sense, these electrons and gamma rays they are the same in this ground-based experiment. Okay.
Thanks.
More questions?
Thank you very much for your talk. I have a question. Is it possible using the data from telescope area energy observatories to confirm any certain anisotropy in ultra-high energy cosmic rays, so to detect the sources?
Yes, this is a good question. Yeah, I think they have detected kind of anisotropy, but this, even for this highest energy cosmic rays, they are already deflected by this magnetic field, both in our own galaxy and the magnetic field in this between these galaxies, between the source to us in this huge this intergalactic space. And we currently do have some knowledge of this galactic magnetic field, but it's still not very in good shape. It's not very complete. And we basically know nothing about this intergalactic magnetic field. So this makes this identification of this, since if you want to locate source, you need to know how these particles are deflected. But if you don't know the shape of magnetic field, this is very difficult. I think this is the most difficult part.
So there are any fixed anisotropy. We cannot talk about it.
No. I think there are a lot of work on this issue. They are using some magnetic field models, and they have some this detected. They use this detected. They use the detected. Sorry, what happened? Okay. They use the detected hotspot. This is anisotropies, and they use this magnetic field models. They trace back their direction of the source, and they claim they find something. But it's not, it's not very. At least in my view, currently it's not very reliable because both of this magnetic field is so uncertain. But this is a quite a popular field, I think.
Okay, thank you.
By the way, I also had a question regarding these two plots. Are they produced for the same energy bands?
No. You see, this is EV, and this is higher energy. I think for this TA hotspot is in higher energy. It's in higher energy.
And if Roger sees this at higher energy?
This is. I'm not sure they can see this because they have different field of view. It's one is in northern hemisphere, one is in southern hemisphere. So.
But it looks they have some data in that region,
Yes, it's a nice question. Yeah. I think the joint analysis is ongoing. It's ongoing. They are doing that. I think.
Yeah. So I was also wondering in this regard if there is an agreement between different gamma rays or cosmic ray experiments and anisotropy.
Gamma rays can do little in this energy band currently, but of course, this Alger and TA, I think they are doing kind of joint analysis at this stage. Yeah.
Other questions, please?
Thank you very much for the talk. I have actually two questions, and the first one is about the second last plot when you had one blue and red curve, and I didn't get the meaning for the red curve and how it was plotted.
Oh, you mean this?
Like almost the very last slide. Yeah, exactly.
Okay. Okay.
This one.
Okay, thanks for the question. So this I don't have time to talk about details. So this plus here, this the dot here is this our measured cosmic ray density in different this galactic-centric rings. So this is different to this galactic center, and this blue curve here is the distribution of supernova remnant. This is from kind of current catalog. And this one is from this distribution of OB stars, this massive stars, this living star. So because it seems here its peak is more consistent with this OB stars rather than supernova remnant. Yeah. This is the idea of this. And I will talk later about this idea of this massive star clusters as an alternative cosmic ray sources and together with this supernova remnant.
Why there are so many peaks?
Statistics, yeah. And because OB stars, massive stars are very difficult to detect in surveys. They are all located in this very high extinction regions. You need this infrared survey to do that, and this kind of survey is not complete at all in our galactic plane.
Okay, and the second question is about spectrum of cosmic rays when you showed two knees. On the plot, and I was interested in the plot chart. So, what is the value of this plot, and why is it existing there?
You mean this one?
For example, yes.
Yeah. Its value, I think the value also before the knee and above the knee is different for different measurement. But currently, this most accurate measurement from LASSO is about 2.7 before the knee and 31. That's 3.1 after the knee. So it's there are softening of about 0.4. The reason is not very clear, and I think there are a lot of models on this. Because in fact we don't know the exact rhythm of the knee. I think someone argued that this is because this acceleration limit of some kind of source population in our own galaxy. And then in this case, but this is also related to this composition of the knee, because if you assume this acceleration is rigidity dependent, the different but this is a measurement of total energy. So this also dependent on this composition of your acceleration cosmic rays. So this is you can have different combinations to explain these features, but it's not there's not a consensus, I think.
So it's just quite a long region where nothing is changing, and the constant is not really fundamental.
It can be not very fundamental, but it is the first very significant turnover of the spectral shape. So that's why it's in tradition it's a very important region in cosmic ray study.
Thank you.
So basically, if there is no new mechanisms like these knees, then you just expect e to the minus 2.7,
yeah.
and you multiply by e to the plus 2.7, and you should get the plot.
Yeah, flat.
Yeah, so this is just an artificial.
Yes. That's true. That's true. Yeah, just for illustration. Yeah.
So this is a comment that when you say the interstellar media energy density, that means the kinetic energy. If you take the rest mass, for example, dark energy, dark matter.
No.
Mass,
I
they are
don't
all
take that.
kind of-
Yeah, I don't take that. Yes.
Right. Okay. So can you go back to this ecosystem, the starburst cycle, so on and so forth? I just want to try to understand. Later on, you had this H1, H2, blah blah blah, all the way to stars. Yes.
Yeah.
Tell me, where does, I can understand that in this region there's a lot of cosmic ray being generated. But how does you go backwards saying that the energetic cosmic ray causes?
Not courses. I think another word, regulate, is more proper.
Okay.
It's not course. I think it's in this process, this dense H2 to stars. So in this process, this the dense gas begin to collapse due to this self-gravity.
Right.
But in this process, you have a lot of things a lot of force to against this tendency, like this pressure, magnetic, for example, the magnetic field pressure.
Photon pressure.
The photon pressure.
Sure, yes.
And this, for example, this magnetic pressure that depends heavily on this ionization rate of your gas. The ionization of this gas is determined directly by the density of cosmic rays in this region, because other things cannot enter these dense regions. This is why they use. It's not cosmic ray begin this process. It's cosmic ray. They set some initial conditions, and I think they kind of regulate this process. It's not governed. Yeah.
If you think about it, it's hydrogen and then start getting hotter and hotter.
Yeah.
I mean, once the temperature gets high, the ionization, the plasma happens by itself. I'm just wondering if this cosmic ray, just in order of magnitude, could make a difference?
Yes. There are some investigations, but it's pure theoretical. It's an observation. But they argue that if this cosmic density is higher, they can have very significant impact on this initial mass function of these stars. So I think their conclusion is that if the energy density is higher, the energy density of cosmic ray is higher, this IMF tends to be top heavy. This means there should be more massive stars rather than these small stars. Yeah.
Okay, thanks.
Very good. Yeah.
Okay, so I think we have to conclude now. Let us thank the speaker again. Thank you very much.